Imagine we have a point in 2D space with xy coordinates 3, 3, and another point at 6, 6. Now imagine that we draw an arrow starting at 3, 3 and ending at 6, 6. An arrow with a starting point and an ending point can represent a mathematical construct known as a vector. A vector contains two key pieces of information, a direction and a magnitude. This vector, represented by our arrow here, has a well-defined direction because we know where it starts and where it ends. We say that it has its tail at 3, 3 and its head at 6, 6. This vector has a well-defined magnitude as well because we know how long it is. The word magnitude simply means size or extent. A vector's magnitude is simply the arrow's length. So if a vector contains direction and magnitude information, how is that information stored? Well, similar to 2D coordinates, which are stored in an ordered pair, a two-dimensional vector has its own pair of scalar values, and we call these the vector's components. A two-dimensional vector has x and y components. So how do we figure out the x and y components of this vector? Let's talk about that. So we have 2 points in space and an arrow connecting one point to the second point. And we know that this forms a vector. But what are the vector's x and y components? How do we calculate that? Well, it's actually quite simple. We know that the tail has location coordinates 3, 3, and the head has location coordinates 6, 6. Let's just start with the x component of our vector first. The x component of our vector is the distance we have to travel in the x direction to get from the tail to the head. Now we know the tail's x coordinate is 3, and we know the head's x coordinate is 6. So to calculate the x component of the vector, we simply need to calculate this distance here. Now, if you're intuitive, you may see that it's 3. But the formula is to simply take the x-coordinate of the head, which is 6, and subtract the x-coordinate of the tail, which is 3. And that gives us 3. And so we know the x-component of our vector is 3. So we can write that right here. Now we calculate the y-component in the same way. We take our y-coordinate of the vector, which we know to be 6, and subtract the y-coordinate of the vector's starting point. That's 3. So we subtract 3 from 6, giving us 3. So we know this distance in the y direction from the head to the tail is 3. So our y component is 3. And we can generalize this into a formula that works for all vectors. If we have points 1 and 2, and we know their coordinates, we can simply perform subtraction. We can take point 1, which has coordinates x1 and y1, and we can take point 2, which has coordinates x2 and y2. If we know these coordinates, we know the vector from point 1 to 2. The general formula for the vector starting at point 1 and ending at point 2 is as follows. We take point 2, we get its x-coordinate, x2, and we subtract the x-coordinate from point 1, x1. This gives us the x-component of the vector from point 1 to 2. And for the y-component, we do the same thing in the y direction. We take point 2, take its y-component, y2, and we subtract the y-component of point 1, y1. This gives us the vector from 1 to 2. So if you ever have 2 points in space, you can always calculate the components of the vector from one point to the other point. When we take the x components and we subtract them and we take the y components and subtract those, and that gives us x and y for the vector. Now, once we know the components of a vector, we can then check to see if it's equal to another vector. Any two vectors that have the same components are equal. Now, I want you to realize something very important. The components to this vector have nothing to do with its location on the xy plane. If I have another vector at -3, -3, so its tail starts at -3, -3, and its head ends at the origin 0, 0, then we have a vector from -3, -3 to the origin 0, 0. Let's calculate the components for this vector. So if -3, -3 is 0.1 and 0, 0 is 0.2, then we can use our formula to calculate the components of our vector. We can say that the vector from 0.1 to 0.2 equals x2 minus x1 and y2 minus y1. Let's do the math. The origin is 0.2, so x2 is 0, and x1 is -3. So we're going to subtract -3. That gives us the x component. And the y component looks similar. y2 is 0, and we're subtracting x2, which is -3. Now, 0 minus -3 is +3. And for y, again, it's 0 minus -3. So again, we have +3. So this vector from 0.1 to 0.2 is the vector 3, 3, which makes sense. It takes 3 units to travel in the x direction from its tail to its head. And it takes 3 units to travel in the y direction from its tail to its head. It has the same exact components as our other vector here. This vector is also 3, 3. So even though the vectors have different starting points in space, they are the same vector. And I could draw a 3, 3 vector anywhere in this plane, and it will always be the same vector, regardless of its starting point. So the only characteristics of a vector that make it what it is are its direction and its magnitude. And any two vectors that have the same components have the same direction and the same magnitude. Therefore, they are the same vector. So in summary, we've learned that a vector has two key pieces of information, a direction and a magnitude. And we've learned that it has x and y components, if it's a two-dimensional vector, and it has 3 components, x, y, and z, if it's a 3-dimensional vector. A single numerical value is called a scalar, and you must have at least 2 dimensions for a numerical quantity to count as a vector. We've learned that 2 vectors are equal if their components are equal. If 2 vectors have equal components, then that means their direction and their magnitudes are also equal, and this would mean that they are the same vector. We've also learned that we can calculate a vector's components by subtracting 0.1 from 0.2 for the x and y coordinates in 2 dimensions. So for 2 dimensions, we have this handy formula. So now that we know what vectors are, let's do a couple of practice exercises.